This is a lesson on wave on a string, which is an application of 2D waves in the Introduction to Waves and Simple Harmonic Unit. In a prior lesson, I had talked about properties of waves, most important being their velocity, which is related to their wavelength and frequency, the fact that they carry energy from point A to B, and also the different types, whether the material carrying the wave oscillates perpendicularly to the wave velocity or parallel to it. And I'm going to remind you that any pulse can be considered a wave with a wavelength, but a periodic wave is a special case of simple harmonic motion and will follow those properties, including the angular frequency being related to the frequency and the period of the periodic wave. 2D waves are a special case of simple harmonic motion. 2D waves are defined to be waves which extend in 2 dimensions and oscillate with time. Okay, so I had covered the idea of a one-dimensional wave. And with a one-dimensional wave, we have dislocation of a medium from a central location in undisturbed position. And when we're looking at a 1D wave, we consider only one location, such that that material oscillates at that one point in space. When we look at a 2D wave, instead, what we're going to consider is that this wave moves through space in 2 dimensions. Its velocity will be in one dimension, and the location will be in the other dimension. So I'm going to rename this. Instead of having x be the vertical direction, I'm going to call y the vertical direction. So this is a y, this is a 2y, and this is a negative y. And so we get the model of a 2D wave. There is a time, right? The wave will oscillate through time, and for any position x at some point in time t, so I may look at this is point x, through time, as the wave moves past that point, the displacement of the particles in that wave will change, and that's the y direction. So you see that the two-dimensional mathematical model for the wave has 2 variables, an x variable, where along the wave are you, and in time. And the displacement is perpendicular to that, or if you have a longitudinal wave, it's in the parallel direction to the propagation of the wave itself. And so those are the 2 variables in that equation. So that's 2-dimensional waves. A special case that I want to focus on that is common in this curriculum is the wave on a string. The wave on a string, and I put a picture over here with the reference, is a 2-dimensional wave. So we can see all along in this direction, and I am going to call this the x direction. The wave propagates along this direction, and its displacement is perpendicular to that. So that's the 2D wave. It's a transverse wave because it is perpendicular to the direction of propagation. The speed of the wave, as you can imagine, if there's a string, it depends on the tension in the string and how heavy that string is. A heavier string or rope is going to be harder to move and will have a lower velocity. So when I look at the equation for the velocity of that wave on the string, it depends on the tension, the force of tension in the string in newtons, the mass of the string in kilograms, and the length of that string. So there's the mass per unit length, mu here. And yes, it's another mu, Greek letter mu. It's a lowercase Greek letter. Here in this situation, it's mass per unit length. So you may see that in different textbooks, or it will be given to you in a problem because that's a standard way to measure string. We don't usually think of taking a string and measuring it. We think of like a linear mass density, just like we might think about a volumetric mass density, where it's true for all parts of that substance, right? So this linear mass density would be true for all parts of that string, and I don't have to actually measure the string that way. So I have picked out a couple of problems to work on this, to look at the equation. The first is a cello string, and I put a guitar here in order to help us imagine what's going on in the problem. This isn't a cello, I am aware. A cello string 0.075 meters long has 220 hertz in the smallest frequency allowed. So the smallest frequency allowed, and that's what I put the picture here. When I think about the wave on a string, and you saw this in the previous slide, I can have different wavelengths of waves on that string depending on how fast I vibrate it. And we'll get into standing waves in a few more lessons. But in the lowest frequency allowed, the fundamental frequency, the wave will, or the string will just oscillate very simply up and down, and the two endpoints of the cello, or wherever it's attached on whatever instrument, will serve as the ends of that. And when I look at this wave, this wave is only half a wavelength. If I wanted to make a whole wave where it goes up and then goes through zero, goes down, right? This is a positive amplitude, and then this would be a negative amplitude. That would be a whole wavelength. The wavelength of this wave is going to be 2 times the length. Okay, so when it says smallest frequency allowed, those are the sorts of things that we're looking at, just to lay this out. So I have an idea of what's going on with the wavelength and the length. So they say the length is 0.75, and so the wavelength is actually going to be 2 times that. Okay. Part A asks, find the wave speed along the vibrating string. Well, I have a frequency and I have a wavelength, and I didn't put this equation on the slide here, but the velocity of a wave is lambda times the frequency. So I can plug those numbers in. I have both of them. The wavelength is 2 times the length of the cello, and the frequency is 220 hertz. So I have a meters and I have a 1 over second, so I get the right units, and the velocity of that wave on that string is going to be 330 meters per second. So that's pretty quick, but we can imagine that for a cello, the string will vibrate very, very fast, and so the wave will actually travel very fast down that string. Part B asks, find the tension in the string if it has a linear mass density of 16.5 grams per meter. So there's the linear mass density. This means M over L. So mu equals M over L, and that is, I'm going to convert to kilograms. It's given to me in grams, but I want it in kilograms. So kilograms per meter. So they give me that value. I know the velocity, and they're asking for the tension. So I'm going to solve this equation for the tension. I'll square on both sides and then multiply by the mass density on each side. So I get the tension equals the velocity squared times the mass density. I already know the velocity, 330. That needs to be squared as a quantity, and then I'll multiply by the linear mass density. And when I run this through the calculator, I get actually a pretty large number. These strings are strung pretty tightly, so that's about 1,800 newtons on there. And another thing I want to point out here, I've seen this in other problems, is they'll ask like, how much force does the neck needs to hold? And when I think about that, 1,800 newtons for one string, and if you have a 5-string instrument, that would be, the neck would need to hold 5 times that force. So that material needs to be very strong in order to hold that string taut in order to make the notes. So that's an interesting problem. The next example I picked out is finding the length of a string. The mass of a string is 5 grams. It is stretched so that the tension in it is 180 newtons. A transverse wave traveling along this string has a frequency of 260 hertz and a wavelength of 0.6 meters. What is the length of the string? Okay, so I saw a lot of information in here, and I'm going to write it out. The mass is 5 grams, so I'm going to convert that to kilograms. The tension in the string, they give me 180 newtons. They give me a frequency, 260 hertz, and a wavelength. And I'm going to note right there, just when I write these two quantities down, that this allows me to find the velocity of the wave. Lambda times the frequency is the velocity of the wave. They give me mass and tension, and when I think about all those things, I have everything in there except what they're asking me for is the length of the string. So I'm going to solve this equation for the length of this string. I'm going to do a couple of steps of algebra here, square both sides, and I'm also going to, instead of dividing by this fraction, I'm going to multiply by its reciprocal, so I'll get L over M. I'm going to solve this equation for L, so I get L equals mv squared divided by the tension. I'm going to plug all this in. I get 0.005 times the 330 quantity squared, and that gets divided by 180 newtons. And when I solve this, when I run all these numbers through the calculator, I get 0.676 meters. So when I look at this number, that's about 68 centimeters. And I know that the string is about 5 grams, so that's a pretty slender string.